Welcome to lesson 5.2 and 5.3 video notes. The learning targets that you can find the circumcenter of a triangle in the coordinate plane. It's going to work out very similarly to how we did it in the exploration. You can use a circumcenter theorem to solve for missing parts. That's probably one of the most critical, using the circumcenter theorem to solve. Use the Incenter, that should be one-word theorem, to solve. Use the Centroid theorem to solve for missing parts inside a triangle, and to understand and describe the difference between circumcenter, incenter, orthocenter, and centroid, which you should already be able to do from our exploration and just the basic vocabulary of those terms. Finding the circumcenter of a triangle, and by the way, the video notes probably will not cover this last one. I will probably ask you to do this in groups in class. Finding the circumcenter of a triangle, we're going to graph the triangle, so we plot the points. We're going to find what's the circumcenter made of. You should know this: perpendicular bisectors for two of the two or three, you could do it for all three, of, actually it's probably finding the equation. Solve the systems of equations, find the equation for two of the perpendicular bisectors, solve the system of equations, find where they intersect, and verify by graphing the third equation. Now, the ones that we have in this particular case that we're going to look at, we will have a couple where we're going to follow these steps. You're going to have to find the equation by using a point and the slope, and using point-slope formula to figure out what you need. But for now, these ones work out very nicely. 10, 0, 0, 0, 0, 6. So I graph this. I should probably get my ruler out. And lo and behold, I have a right triangle. The right triangle is the easiest one to do. You already know where to anticipate that the circumcenter will be located. Half of 10 is 5, so I would find the midpoint. If I were doing this and it weren't a right triangle, I would find the midpoint of this. I would find the slope of this line. Well, the slope of this is 0. So the perpendicular slope is undefined. So there's a perpendicular bisector. Here, the distance of this is 6, so the midpoint's at 3. It has an undefined slope, so its perpendicular line will have a slope of 0. And two of them, that's the intersection point right there at 5, 3. 5, 3 is the location of the circumcenter. I also can check this finding the midpoint of this, which just so happens to be 5, 3, because 10 to 0, half of 10 plus 0 is 5, half of 10 plus 6 is 3. And the slope, which is down 6 over 10, is negative 3/5. So I would want to do positive 5/3 as my slope if I were having to graph this line. 1, 2, 3, 4, 5, 1, 2, 3. Perpendicular line, the third line that's perpendicular to that is this one. So now I have all three perpendicular bisectors graphed. And there's my triangle. And I have the circumcenter right there. If I were to drop a compass on this point and on the point up here, and as long as I don't make a mistake with my compass or if it doesn't shift, mine has been shifting today. It should, see, it shifted just there. It should intersect all of the vertices to circumscribe the triangle. And you can see that it does that here, here, and here. It now sits on it. I'm going to ask you to give this one a try. You should be able to find it pretty easily. Take a moment to pause the video. Welcome back. At 0, negative 9, you should have plotted a point. At 0, 0, you plotted a point, and at 8, 0, you plotted a point. You connected them with a ruler and found the midpoints. Now, because one of the sides is horizontal, and we're in luck, one of the sides is also vertical, it's very easy to find the midpoint. This midpoint is 8 or 4. This midpoint is negative 4.5. We draw a perpendicular line to those, and we find our circumcenter at 4, negative 4.5. We verify that by drawing the third perpendicular bisector, which lo and behold, because the distance from here to here is negative 4.5, and from here to here is 8, and So we would do 0 plus 8 divided by 2, 0 plus negative 9 divided by 2. We get this point, which is where they all meet. The slope of this line is up 9 over 8. So I would want to reverse that slope and actually go down from this point down 1, 2, 3, 4, 5, 6, 7, 8, 9. And I would, all right, and then we're going to need to, this is where it's going to get difficult for this particular one. We need to rescale or have a larger graph. We'd need to go, I didn't need to go down 9. I need to go down 8, 1, 2, 3, 4, 5, 6, 7, 8. And we're going to pretend it's there. Hopefully it's not scaled very well. And then right 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we connect those points. And that's sort of perpendicular. It looks like a perpendicular bisector. We know it's definitely the bisector. The circumcenter is right there. We already knew it. We were just verifying it with the other midpoint and slope. We're not always going to know. It's not always going to be on here. This is only working, as you know from the exploration, for right triangles. So we've looked at how to graph a circumcenter in the coordinate plane. We're now looking at how to apply the circumcenter theorem. The circumcenter theorem says that, basically, I will summarize it in a second, but if, so we're basically given the 3 perpendicular bisectors of a triangle is what's given to us as the hypothesis. If 3 perpendicular bisectors concur at a point, we already know that point is called the circumcenter, then that circumcenter, you can get the formal definition from the book if you want, but here's what you need to know. Circumcenter is equidistant to all vertices. So I have this triangle. I'll draw the right triangle. Well, it's sort of a right triangle. And we have our circumcenter because it was formed by the perpendicular bisectors. It's not quite a right triangle. And so what it's saying is that, hey, remember that theorem, even though we're not going to see the circle. Remember a circle would circumscribe this, and it would touch every single vertex of the triangle? Well, if it touches every single vertex of the triangle, and this is its center, then the distance from the circumcenter to this vertex is the radius of that circle. It's also the distance from here to here and from here to here. Now, it's not always going to look like it falls on that side. That only works for the right triangle. So, but that's what it says, that the circumcenter is equidistant to the vertices. So if we have a center, the circumcenter, formed by 3 perpendicular bisectors, then that center is equidistant to the vertices. So looking at the application of the circumcenter theorem, DE, EG, and FG are all perpendicular bisectors. DE, wait, why is this? Oh, DG. There's DG. So this has been bisected. EG, oh, that's it. It's AE, the same thing. That's been bisected and is perpendicular. And FG. So these have been bisected and perpendicular. Kind of looks like an equilateral triangle. May or may not be. I'm not really sure. But I do know those two are definitely congruent because it was bisected by a perpendicular bisector. So are those two. So are those two. Now, it says find GC. The distance from G to C is a radius of the circle if this were, since that is the circumcenter of the circle that would circumscribe that triangle. Well, all I have to do is look at the other 2 radii. This one right here is pointing to it. It says it is 13.4. There are other lengths I could find on this. Knowing that this is 13.4 and this is 7.3, and we have a right triangle since it is a perpendicular bisector, I could always solve for this piece right here, BE, using Pythagorean's theorem, and EC would have to be the same length. So I could find the full length from B to C. I'm going to ask you to try to find GM, GK, and JZ in this triangle, knowing that these are perpendicular bisectors. ZM, KZ, and LZ are perpendicular bisectors. So take a moment to pause the video and see if you can find those values, those distances. Welcome back. From G to M, knowing that this is a perpendicular bisector, GM is one of the pieces of GL which has been bisected. So GM is 14.5 units. We're not sure what the units are. They didn't give them to us in the picture. GK. GK, where is that? That's right here. Now this 19.9 is actually pointing to this piece right here. So that's important to note. That's why that little mark is there. KH is 18.6, and since this side has also been bisected, GK also has to be 18.6 units. And now they ask us for JZ. JZ is the distance from the circumcenter to a vertex. Circumcenter to the vertex, the circumcenter of the vertex is equidistant. Circumcenter is equidistant to all vertices. So it's going to be the same as GZ. JZ equals GZ equals HZ. All three of those will be a value of 19.9 units based on what's given in the picture. That's how we apply the circumcenter theorem. We're going to cover the other two theorems, incenter and centroid, in this video. Recall from the vocabulary what an incenter is. An incenter is formed by the three angle bisectors. So in our triangle, we have angle bisectors. We've got those angles congruent, and those angles congruent, and these angles congruent, and that's the incenter. Why is it the incenter? As you'll recall, it's because it will be the center of a circle that would be inscribed in the triangle. Well, if the three angle bisectors intersect at a point of concurrency, you can get the formal definition from the book if you would like it. Then, that point, which we know is the incenter, this is the thing we need to know about this theorem. The incenter is equidistant to all sides. Equidistant being the distance on a perpendicular path from that center. So I have this triangle in here, and I'm going to try to sketch this as best I can. There's one of the angle bisectors, there's the other, there's the third. We're going to pretend that big point is our incenter. Well, if that's the incenter, then that's because it's the center of a circle that will touch these points. On the perpendicular path to those sides, the circle will be inside, completely inside. Mine kind of goes outside. It's not supposed to. So what that means is, in terms of this picture, if I call that C and this A and this D and this B, that means that AC equals DC equals BC. The distance from this point to this side, distance from this point to this side, distance from this point to this side will all be the same. That's what the incenter theorem says. So these are pretty basic if you know the theorem. Now you got to remember we're dealing with angle bisectors, so I may ask you to find angles, not just side lengths. So they're asking us, knowing that these are angle bisectors and we can see their point of concurrency, the other angle bisector will also meet there. We know, hey, the angles have been split in half, so if this is 50, then this is also 50 degrees right here. We don't know this yet, but we do know that they are the same. And we know that the distance from P to Q is 5, which means even though they didn't draw it for us, the distance from P to MN will also be 5, and the distance from P to LN will also be 5. So they have to be the same. So the distance from P to MN is 5 units, whatever the units are. Now when they ask us to find angle PMN, that's this little piece right here. I'm going to put an X in there. Well, I know this angle is 20. I now know, since this angle was bisected and that piece is 50, that this whole angle here is 100. So 120 degrees, using the triangle sum theorem, 180 minus 120 degrees leaves me 60 degrees for all of angle M. So if all of angle M is 60 degrees and I'm splitting it or bisecting it, then angle PMN, that little piece right there, has to be 30 degrees. Take a moment to try this problem, very similar to this, using the angle bisectors and the Incenter theorem. XQ and XR are angle bisectors, which means this point right here, X, is the incenter. Well, if that's the incenter, then the distance from X to Y, which is 19.2, is the same as the distance from X to PQ and the distance from X to QR. Or, yes. So when they ask for the distance from X to PQ, we know that it is 19.2 using the Incenter theorem. Finding angle PXQ, PQX. PQX I will trace in pink, is this angle up here. If I find the whole thing, I know it's been bisected because these are formed by angle bisectors. We know that all of P is 52 degrees. Since this little piece of angle R is 12, that makes this piece 12, so all of R is 24 degrees. Using the triangle sum theorem, we're going to subtract the 12 and the 52 from 180, which leaves us 116 for all of angle Q. And since we're bisecting it, PQX, which will be half of that, which is 58 degrees. Lastly, we're going to look at the centroid theorem. The centroid theorem is not as straightforward. It doesn't talk about things being equal or congruent. It actually has a slightly different relationship, but it will give us an equation to be able to solve for sides. And it says basically if a point is the center, or is the centroid of a triangle. So I might not tell you on your quiz or on other assessments that it's the centroid. I may give you a picture where you can determine that it's been formed by the medians, because that's what you're supposed to know, the centroid's formed by medians. And so you're like, hey, there's my picture, and I've got the midpoint going to the vertex, and the midpoint going to the vertex, and the midpoint going to the vertex. Hey, because I know that, not that it's perpendicular bisector, but a median, that's going to be the centroid. So somehow, some way, you know it's the centroid, whether it says centroid or not. Here's what happens when we have that picture, and I'm going to try to be a little bit more clear and not be as sloppy with my sketch. Here's this midpoint. There's the line connected. I'm going to use my ruler. Here's this midpoint roughly. I'm going to connect it. Here's this midpoint roughly. Not exactly. It's actually down here a little bit more. There is my centroid. Because it is the centroid, these distances are not equal. This is not like the center of a circle. It does not touch the sides. There's no inscribed circle. There's no circumscribed circle. It doesn't touch the vertices. Those are strictly for incenter, touching the sides, and circumcenter, touching the vertices. Instead, there's a relationship between this piece and this piece of the median that's separated. And even though they're not equal to any of the other pieces on the other medians, there's a relationship between this, the same relationship exists between this longer piece and this smaller piece on that median. And even though those pieces, none of those pieces are equal, per se, they might be on certain triangles, this piece and this piece have the same equation or relationship. Okay, so I'm going to give this triangle a name. We'll call it ABC, and we'll call these midpoints X, Y, and Z. We'll call our center P for this. Our centroid we'll call point P. Well, that relationship is the following, that the centroid is 2/3 of the way from the vertex to the midpoint, or 1/3 of the way from the midpoint to the vertex. You're going, what? What does that mean? In terms of the equations, let's look at A and X. The distance from A to P is 2/3 of AX. This is 2/3 of the full segment. The distance from X to P is 1/3 of AX. So basically, this thing cuts it into two pieces, not equal pieces. It was not bisected by any means. 1/3 of the median lies on this side of the centroid, 2/3 of the median lies on this side. So we're going to use that knowledge. By the way, that's the same thing for BP and to BY and PY to BY, CP to CZ and PZ to CZ. The smaller piece is 1/3 of the total segment. The longer piece is 2/3 of the total segment. So let's take a look at these application problems. We see that these are medians. There's no perpendicular symbol, so they're not perpendicular bisectors, so this is not a circumcenter. We said they're medians. We see that they're medians because they're midpoints connected to vertices. You see midpoint to vertice or vertice to midpoint, you know that this is a centroid and that you need to use the centroid theorem. Well, they're telling us that RL, the whole thing of RL, is 21. And they want us to find LS. LS is the longer piece. It's vertex to centroid. So LS is 2/3 of the whole thing, RL. 2/3 of 21. 21 over 3 is 7 times 2 is 14. So LS is 14. So this piece right here is 14, which means this piece is 7. 7 plus 14 adding to 21. 1/3 of it existing here, 2/3 of it existing here. They also tell us the distance from S to Q, and they tell us that that is 4. Well, that's part of NQ. In fact, it is 1/3 of NQ. So SQ equals 1/3 of NQ. Well, we know SQ is 4, so if I take that 1/3 piece and multiply by 3, I get 12 is the length of NQ. So now I know this piece is 12, this piece is 4. Together, the whole thing is 12 plus 4, or 16. Please take a moment to pause the video and try this for the next problem. This is our last problem of the video notes. In triangle JKW, we have vertex to midpoint, vertex to midpoint, vertex to midpoint, not perpendicular bisectors. We have to pay attention to when it's perpendicular bisectors versus vertex to midpoint. So those are medians, which makes Z the centroid. Because Z is the centroid, we know that this theorem applies. The longer piece of the centroid is 2/3 of the whole thing. The shorter piece is 1/3 of the whole thing. They have told us that ZW, the shorter piece of KW, is 7. ZW is 1/3 of KW, the whole thing. Well, to solve for KW, we multiply by 3. And we get that KW is 21. We were asked to find KW, so that's 21. We could just as easily be asked to find ZK, which would be 2/3 of 21, 14. We're also asked to find LZ. LZ is a piece of LX. They tell us that LX is 8.1. So LZ is the longer piece. It is 2/3 of the whole thing. The whole thing is 8.1. So 2/3 of 8.1, or 2/3 of 81 divided by 10. That's going to be 5.4. That would be 54 divided by 10. 5.4. So now we know the lengths of the pieces that they asked us to find. These theorems can be added to what you know or what you need to memorize. You're supposed to know how a centroid is formed, how to draw it. Now you know this theorem about it, what you're supposed to know about the pieces of the medians. The incenter, now you know what you're supposed to know about the distance from the incenter to the sides. And circumcenter, what you're supposed to know about the distance from the circumcenter to each vertex. This concludes the video notes for 5.2 and 5.3. We will pick up at you being able to describe the differences between circumcenter, incenter, orthocenter, and centroid. Have a great day.